Hello everyone, this is Space Café podcast, and I'm Markus. I want you to take a pencil and sketch out the strangest creature you can imagine. Try a little harder, you can do a lot better. I mean, the strangest creature you can imagine. That's kind of what my father's biology teacher did many, many years ago to get his students excited about the creatures of the deep sea. Draw the strangest creature and you can be sure that it exists in one form or another down there. I like this image because it tells a gripping story, a story that there is something out there that is larger than us, not necessarily physically. Okay, that may be too, or cognitively, that for sure too. But that there is so much more to discover out there in our immediate neighborhood, off the beaten track of our everyday lives. I don't even manage to break my daily routines and start my daily commute on the opposite side of the street, just for the sake of a change of perspective. Before I deleted the automatic records of my movements from Google search forever, yes, I didn't know I was being recorded. It turned out that I had lived a monotonous life over the years. Same routines, same destinations, day in, day out. How can I let something new into my life? Yes, I know there are books and good movies and good conversations, but just for the sake of the argument. If some of you feel the same from time to time, I'll try to get you out of your veil of tears with today's episode of the Space Café podcast.
So you ready?
Yep, all cool. Good.
So thanks, Matt, for taking the time.
Thanks for having me.
My guest is Professor of Astrophysics at the University of Toronto and a visionary sound artist who gives scientific knowledge a new dimension of understanding. A true tour de force through space and time, in its most literal sense, awaits you right now. Ladies and gentlemen, please welcome Professor Matt Russo. Fasten your seatbelts. Let's go.
Now that we work for NASA, it's brought our work to a much larger scale, and people are responding. So it's turning into a career.
So what is it that you do for NASA?
So we do different types of sonification. And one currency of NASA and astronomy in general is images, amazing images from space telescopes. And those images are not accessible to people who are blind or visually impaired. So part of the job is making an audio version of NASA's iconic imagery.
Like what?
So
can you give me an example? By the way, do you have samples of your work here we could listen to?
Yeah, on my laptop.
Why not?
Okay, let's start.
Let's just listen to it first and not say anything about it.
Sounds good. Wi-Fi's a little slow.
Okay, no
coming.
problem.
Yeah.
No problem.
Yeah.
Okay, that sort of reminds me of Stanley Kubrick. What could it be?
A particular Kubrick soundtrack?
Well, it reminds me of Space Odyssey.
Yeah. Yeah, it's interesting. Many people think that our sonifications sound like, 60s and 70s sci-fi.
Yeah.
Because we are using similar synthesis techniques to how they would make out of this world type sounds for those. In our case, we're actually using data from space to generate them. But
so what was that?
So this is sound waves in the Perseus galaxy cluster. So
okay.
It's very different from all the other sonifications. It's very special because there's an image taken in X-ray light that actually shows the ripples of real sound waves in space.
But there's no sound in space.
But that's not quite true. So there can be sound wherever there's a gas or a medium to transmit it, and space is not a perfect vacuum. In this case, it's a galaxy cluster. So it's very, very diffuse gas, but over hundreds of thousands of light years, there's enough gas for very low frequency sound waves to travel. And these waves are so low frequency that each crest of the wave would take about 10 million years just to pass you. And an audio wave takes like a fraction of a second to pass your ear for your brain to hear it as a sound. So these waves have to be sped up by many times.
So if you were to fly around that very location, you wouldn't hear anything, right? If you opened your visor and listened to...
That's right.
So you wouldn't hear anything?
You wouldn't hear anything.
Okay.
For the two reasons. So one is that there's just not enough gas for our ears to be sensitive enough to pick it up. But the other reason is that it's happening on such a large time scale that it's basically lower than our human hearing range by many orders of magnitude.
Can we listen to it again?
Sure.
Tell me again how that is sped up to make it audible.
Yeah, there's a few things going on. In the black hole is generating sound waves. The black hole has a jet which pushes on the gas that generates sound waves which travel out in all directions. And what we're doing in this is listening to the wave along each direction. So along one direction, you get a certain tone, and then we're kind of sampling all the directions to hear a tone. But in that process means we're speeding it up by about 58 octaves. So that's like 58 musical scales to get it into a range.
Wow. But it sounds like what I would imagine a black hole to be menacing and dark. Is that artistic freedom, or is this what this place sounds like?
Yeah, it's a little of both. So there is artistic choices. There are artistic choices that have to be made. And so one is do we scale it up, or one artistic choice is how much do we speed up time? Do we speed it up so that it's a low note or so that it's a high note? And in this case, in reality, this is the lowest note we've ever detected in the universe. So we sped it up just so that it's still a low note in our hearing range. And that helps it sound more ominous. But we thought that helped tell the story of what it actually is.
Wow. So how far away is that?
This is not even in our galaxy. This is tens or hundreds of millions of light years away.
Wow. And so where does the image come from? Hubble?
This image is a Chandra
X-ray.
It's all X-rays. And so we're seeing as the sound waves go through the gas, it heats up the gas and they give off X-rays that we can detect.
Awesome. How did you get into that?
Well, for over 10 years, I was struggling to choose between the worlds of music and astronomy. So I was studying jazz guitar and taking astronomy classes, and then I was studying astrophysics and playing in a band. And it just didn't occur to me for many years that I could just combine those two worlds instead of trying to make either work. I realized I could convert astronomical data into sound, and as soon as I did, there was just a huge reaction from the public and from people who are blind, and it was just so rewarding and fun to do that I just kept doing it.
But you're still an astrophysicist teaching real astrophysics?
Yes,
right?
So I'm still a physics professor. And my other passion is education. So I'm a teacher, and part of what we do with the sonification is use it as an outreach tool to get people excited and interested in certain astronomical images or events.
Mm-hmm. Fascinating. So what are the reactions you're getting, and who is reacting the most to it?
Well, it was really surprising to us because we initially just started doing sonifications because we thought they were fun and interesting. But the public really responds, especially on social media. They're kind of crafted for that. And it's just every kind of person seems to respond. And a lot of the comments on social media are that they weren't expecting to feel so much listening to it, that it was an emotional experience. But the most rewarding feedback is, of course, from people who are blind.
Sure.
So one of our collaborators, Christine Malik, is blind. And she said that listening to our image sonifications gives her the feeling she thinks that sighted people have when they look up at the night sky. It's something that she's never experienced. She can only imagine it. But she says it goes a long way to giving her that experience. So when you hear feedback like that, that makes it all worthwhile if you're giving an experience to someone that couldn't otherwise have it.
Absolutely. So how does that feel to you personally when you listen to your work? Because I feel like you're giving space a voice all of a sudden. So it becomes alive, whatever that means.
Yeah, I mean, I get excited about allowing people to experience one thing in a completely different format, a completely different sense. I just find it interesting that the same information can be represented through different senses.
Mm-hmm.
And I find that it's kind of like a puzzle that exists with the sonification. And so there's information we're collecting from telescopes. We can represent it through images or through sounds. And I just find that whole interplay interesting of how that same information can be communicated in completely different senses.
Let's talk about astrophysics. We're in a very interesting moment in time. Do you think that we're in the process of becoming an interplanetary species? Or is that too early still?
Well, some people are definitely in the process. Some people are trying. I'm not sure it's going to be easy to get the whole world on board for that. I'm not sure if that's a necessary goal. But there's something in all of us that wants to explore. And so I think it's a very natural human instinct to want to explore and discover all things that can be discovered. So I cheer on those efforts to learn more.
Sure. What are you hooked by at the moment? What kind of space mission are you waiting for?
What I'm really excited about is the Europa Clipper mission. Is one of the missions that's sending a probe through the gas plumes of a moon of Jupiter called Europa. Mm-hmm. And there are many moons in the solar system that have global oceans, liquid water under ice.
Like water.
Water, yes. Very, very salty water.
Salt water.
Yeah, it's very, very briny. But it seems to have the conditions required for life. It's got liquid water. It's got an energy input from the tidal interactions of the planets on the moons. But the problem is it's all mostly beneath the ice shell. So there are some spots where there are geysers shooting what's inside the moons to the outside. And there are plans for probes that'll just fly through that cloud and just detect, are there organic molecules here?
Wow. Preconditions
for life or life itself is the dream.
So tell us more about Europa. So you got an ice shield. How thick is it?
It's several kilometers thick. So it's not something they could just land on and dig through. But the ocean itself is hundreds of kilometers deep.
Hundreds of kilometers?
Yeah. There's more water on Europa than all of Earth, even though it's a relatively small.
Wow.
And there are actually several moons like that around the solar system. So even a moon of Saturn called Titan, it looks very different. It's got very different chemicals on the surface. It's got methane lakes for one thing, but we also think that there's undersurface global oceans.
Wow.
So it seems to be a common thing among moons in the outer solar system, large moons. So
that's so incredible. I mean, just imagining the sheer fact that right now, as we speak, there is this celestial body out there with hundreds of kilometers of water underneath an ice shield, pitch dark, and whatever is in this water. Is there a potential for life in that water, or is that science fiction? And what kind of life are we talking about? I guess we're not talking about fish.
Well, there's definitely a potential, but really we don't know. We wouldn't be able to detect it if it is there, even if it is space fish. It seems more likely that if anything, it's some kind of microbial life form. But we really don't know. We just can't access it right now.
Are there any plans to access it, to melt something through the glacier? Or no, it's not a glacier, through the ice shield?
Yeah, I forget the names of the missions. I think there is a proposed mission to do just that, because you can't bring a drill long enough, but you should just get really hot and melt yourself down.
Yeah.
But they're going to start with the flybys and see if it's worth investing in something more serious.
I'm sure was an interesting discussion on Earth and Antarctica. There's a lake called Lake Vostok, and it's underneath the ice shield, a huge lake, a couple of kilometers deep. And the Russians drilled a hole into that lake. And there was a huge discussion if we should do that or not do it, because it's a pristine body of water. Should we drill a hole and spill kerosene into that pristine body of water? So how do you react as a scientist to something like this? Because we would do similar things then on Europa. Maybe not with kerosene.
That's right. Yeah, as a scientist, I would just want to get more information. I want to find out what are the actual risks to neighboring ecology.
Mm-hmm.
So I have to see a more detailed plan. I wouldn't be automatically for or against it.
Or against it, sure. But here's one thing, and I'm so glad you're with me here on the show. On Earth, we have no clue, as far as I understand, where the water comes from. So where does it come from on Europa or wherever on those bodies? So is there any?
So there is a bit of an open question on how our water was delivered to Earth, because it couldn't be primordial.
Yeah.
But with the moons of the gas giants, it's less of a mystery because in the early formation of our solar system, there was water ice at those distances. Mm-hmm. So if you're far enough from the sun, water could collect in ice, mm-hmm. and then that could form into planets and moons. Where Earth is, it's too close to the sun, and so the ice would have been vaporized. Mm-hmm. And so it couldn't collapse into planets the way it did out there. Mm. So the proposals for how water got to Earth, a lot of them have to do with water coming from the outer solar system and being deposited.
Huh. And that's, is that theoretically potable water? Would we be able to drink it?
Yeah. Water from different locations in the solar system has slightly different amounts of different compounds. Sure. So different amounts of deuterium and things like that. And other minerals, but if it's not too salty, you can drink it.
Where does the water come from altogether? How was it formed?
So water is one of the more simple molecules. It's actually relatively easy to form if you have enough of the right constituent parts, which are hydrogen and oxygen, and the temperatures are low enough.
And pressures.
And the pressures have to be right. Yeah, the temperatures and the pressures have to be right. But those conditions are satisfied very easily in forming planetary systems. And so when we look at other solar systems that are just forming, we can detect water there too. And so we think it's a very common thing for there to be water worlds, so planets that are even mostly water in other solar systems.
But the constituents of water, hydrogen and oxygen, they were produced in stars before that.
The oxygen was.
The oxygen, because hydrogen was produced during the Big Bang or after.
That's right.
And where does the oxygen then come from? How does that work?
So as stars burn, they burn initially hydrogen into helium overall.
That's what's happening in the sun.
That's what our sun's doing right now. Yep. But more massive stars go through many stages. Once they run out of the helium that we required, they can start burning helium into heavier and heavier elements. And so if the star is massive enough to begin with, it eventually can form things up to oxygen and carbon, and that chain can go all the way up to iron. Mm-hmm. So you can form iron by nuclear fusion within stars.
Mm-hmm. And how then does the oxygen get out of the star and come into our solar system or wherever?
Yeah. So it's a great kind of circular, life cycle story, is that the oxygen is fused in the cores of stars, but stars eventually die. And in some cases, they can explode as supernovae. And so they expel the outer layers of their material out into space. And when enough of them do that, that dust and gas can collect. And if that gets dense enough, it can reform a new star, now with more heavy elements. Uh-huh. And that can have planets with, rocky planets, and all of the heavier elements can coalesce.
Great. Would we be able to hear a supernova? Would you be able to sonify that?
Well, a lot of what's going on in a supernova is sound waves traveling through the star. Mm-hmm. So if you were in the star itself, had a microphone, it'd be an enormous sound. But from a safe distance, the sound can't travel through the gas very well. So it can't get to you at a distance. But if you have enough, if you have a good mathematical model of what's going on in the core of the star and how it explodes, which is a thorny problem, you could model the sound waves that are propagating through a supernova and try to synthesize that.
Is it true that I heard or I read somewhere that during a supernova, when the outer shell collapses, that collapse is extremely rapid. So it collapses within the fraction of a second. The distance or the entire distance of its radius. Is that somewhat true?
That's right. So it's essentially in free fall. So the inner portions are in free fall. Because gravity isn't strong enough at that point. Gravity is much stronger than the pressure forces in that situation, and so it just collapses under its own weight. And yeah, that happens very quickly. I think it's within seconds.
Seconds.
Yeah.
So you got like a star with millions of miles or hundreds of millions of miles in diameter?
Yes, but only the core itself is really collapsing.
Yeah. The core.
Yeah.
So not the outer crust.
No, it's mainly like a wave that travels through, collapsing part of the core.
Okay.
And unless it's too massive, it'll bounce back. And that's what causes the...
And this is how we get the oxygen, because it bounces back and explodes into
interstellar space.
Interstellar space.
Spews its material out. Yeah.
Wow. How often does something like this happen?
Well, in our own galaxy, with a few 100 billion stars, it happens on average every 1,000 or few thousand years. But since we can see thousands and thousands of other galaxies, they're happening all the time. So at least once a day. I'm not sure on the stats now. But
once a day.
Somewhere in the sky, there's some supernova going off almost all the time.
So what does this look like? Does it look like a very bright light, then dimming off immediately, or what does it look? Because there was last year or 2 years ago, Betelgeuse, where they were expecting, I think this was just the media expecting a supernova happening. I don't know if this was ever a case for science. But Betelgeuse was maybe in the process of producing something like this.
Yeah. So we know that Betelgeuse is near the end of its life. That's why it's expanded into a red giant. But we think it won't actually go supernova until about 100,000 years.
Okay.
So that's why scientists were pretty confident this wasn't the supernova about to happen.
Okay.
But it might be related to its evolution. But Betelgeuse is in our galaxy. And so if that went supernova, you would definitely see it. The star's already naked eye visible. Mm-hmm. It would be almost as bright as the moon for a few days or weeks.
Wow.
But most supernovas we detect are not in our own galaxy. That's very rare. And so the way you detect them is just by comparing images of galaxies kind of before and after and looking for one spot that wasn't there before.
So where would we, in the night sky, go look for Betelgeuse for whoever is interested in that?
Yeah. So Betelgeuse is relatively easy to find. It's in the Orion constellation. And so in the Northern Hemisphere, at least, that's one of the more prominent constellations.
That's the cross.
It's a hunter.
Yeah. Mm-hmm.
In some cultures, it's Orion the hunter.
Yeah.
Many cultures, actually, but not all of them. And most of the stars in Orion are bluish. They're very bright blue stars, but the left shoulder is very red, and that's Betelgeuse.
Blue means extremely hot, if I remember correct.
That's right. They're extremely massive, hot stars.
Like how hot?
So the surface of our sun is about 6,000 degrees, and that kind of gives it its
Celsius or
6,000 degrees Kelvin.
Kelvin, right.
Close to Celsius, yeah.
Enlighten us, Kelvin. How does it translate into Celsius?
They're different by 273. Okay. So for astronomers, when you're dealing with thousands and millions of degrees, you almost never think about the distinction.
It doesn't really matter anymore. It's really hot.
Right. So our sun is about 6,000 degrees on the surface. Those hot blue stars, they can get up to hundreds of thousands and even millions of degrees on the surface in some cases.
I heard that this explosion can produce radiation also. Or am I mistaking this for a black hole? Because that kind of gamma radiation could be an issue to all living things on Earth. Is that a thing?
That's right. That's part of my PhD research was in studying gamma ray bursts. And so when a massive star, when its core collapses, either into a black hole or a neutron star, sometimes that also launches a very powerful jet out the poles. And that jet is going incredibly fast. It's a relativistic jet, so close to the speed of light. And we're not exactly sure, but that can generate very, very intense. It's intense gamma rays. It's a gamma ray jet is what it is.
Gamma ray is never good.
Yeah, so you don't want that pointed at you.
Gamma rays we get in nuclear power plants.
That's right. Any kind of gamma rays are also created in the center of the sun with its fusion.
Mm-hmm.
But by the time they make it to the surface, they're much lower energy. But I
mean, like a gamma ray burst to hit Earth would be an extremely unlikely coincidence, right? So if it happened, it would almost be intentional by someone, right?
Well, for it to be close enough to be threatening, it would be a star that's in our galaxy, but they're so powerful that they don't have to be that close if they're in our galaxy.
Yeah. Uh-huh.
It's just that supernova in our galaxy, they don't happen every day.
Yeah.
And so if they did happen, it probably would not be directly pointed at us. We wouldn't be down the end of the barrel.
Okay.
But it's still possible, right?
Let's go back to music. Can we listen to something? You pick something and you let me guess what it is.
This will be tough. Let's go with...
That sounds like an aurora to me.
Mm-hmm. I've heard Imogen Heap vibes from this.
Now, what is it?
But it's not an aurora.
Yeah.
This is an image sonification of what's called the Chandra Deep Field. Mm-hmm. So it's the deepest X-ray image ever taken. There's something similar called the Hubble Deep Field, an ultra deep field, which is an optical light, but this is an X-ray light. So if you look at a patch of sky where it looks like there's nothing, but you just leave an X-ray telescope open.
It's full of something.
It's full of thousands of points of light, which are the light emitted by black holes in the early universe. So they're emitted by supermassive black holes shortly after the beginning of the universe when things were a lot more chaotic.
Hold on. A black hole shouldn't emit light.
Right. So there's a surface called the event horizon. Uh-huh. And if anything gets past that event horizon, it can never escape. So it can't emit light even.
Yeah.
But the neighborhood around black holes are very active because as matter is falling in, it can create an accretion disk, kind of like a whirlpool. Mm-hmm. And that can get really, really hot, which can give off intense X-ray light. And the exterior of the black hole also spins up magnetic fields, and those can launch very powerful jets. Mm-hmm. So it's not true that black holes only suck things in. Around their neighborhood, they have a huge effect on their surroundings, and they can launch jets at close to the speed of light with very intense very intense energies. And that's what we're seeing across the universe. Some of these points of light are emitted by black holes in galaxies that are about 10 or 11 billion light years away.
Wow. Can we listen to it again?
Sure.
So the different pitches, what the higher ones, the lower ones, are we seeing flashes of black holes?
No.
Hearing?
The way this works is it's an image sonification. So there's a fixed image showing what looks like just thousands of points of light with all different colors. And the colors in the image are indicating the energy of the X-rays we're receiving. Mm-hmm. And so through sound, we're listening to the different energies of X-rays coming from more or less energetic black hole jets. So the lower notes are lower energy X-rays and higher notes are higher energy X-rays.
Huh.
So each note you hear is the light from a supermassive black hole, and its pitch is telling you the energy of that light.
How far away is that?
So it's a range of distances, but some of them reach back 10 to 11 billion light years away. So we're looking that far out into space, and consequently 10 to 11 billion years ago.
Wow. So we're looking back in time. We're traveling back in time. And I guess most of those black holes aren't around anymore.
Well, those black holes probably still exist as supermassive black holes in their galaxies, but they're probably not active anymore. So Our galaxy has a supermassive black hole in the center, but it's not very active. There's not much material flowing into it. But in the early universe, it was a much more active place in general, where things were forming and collapsing at a greater rate. And so a lot of these, they're called active galactic nuclei, these supermassive black holes that are forming intense jets. They were much more common in the early universe when things were still being figured out.
The universe was figuring out itself.
Yeah.
So what to become, what to become.
Yeah, those were like the chaotic teenage years with outbursts, and things have calmed down since then.
Wow. How big are those black holes?
So those supermassive black holes can be about the size of our entire solar system.
One.
Big enough. One. Yeah. Black holes are, it's like the densest you can pack matter, right? But if you have a lot of matter, those can still be large. So if you took the Earth and squished it enough for it to become a black hole, it would be about half a centimeter across. So you can imagine the mass that has to go into making something that's the size of the solar system. It's tens of billions of star masses, solar masses.
Black hole is a strange terminology because it's not a hole. It's the exact opposite. It's not void of something. It's massive presence.
Yeah, and that name is a little unfortunate, right? It gives people this idea that it's just like an opening where you could escape our universe or something.
So it's like tapping on the surface of a table. My finger cannot go into the surface because the surface is concrete, and a black hole will be a lot denser. But in science fiction, we're being told that it is possible to spaghetti ourselves beyond the event horizon into a black hole. That doesn't make sense, because if something is extremely dense, how would that work?
Well, it's not actually solid. It's incredibly high densities, but the way to think of it is the black hole itself is not so much an object, it's a structure of space-time. So it's more like a region of space-time where gravity is so intense that light can't escape. But all of the mass that goes into it does collect into the center, which is either a singularity or something else we haven't understood yet. But all of that would be right in the center of the black hole. The rest of the black hole is just a certain causal geometry of space-time. So you could fall right through that and you wouldn't even notice.
So the very dense thing I was talking about is just a core.
If anything, yeah. It's either an infinitesimal point, or it has some small extent of incredible density, like much more dense than an atom's nucleus.
What would that singularity look like? Is it when like the constituents of matter touch one another or become one, or what's happening?
Well, yeah, all we can say is our equations break down, right? Yeah. So if you look at the density, it goes to infinity at that point. And so that's telling us that we don't understand everything. And so we need basically a quantum theory of gravity to understand what is actually going on at such incredible densities and energies. We don't have that answer yet.
But I guess someone is working on that.
There's a lot of people working on that, but it's a hard thing to study, as you can imagine. It's not something you can test experimentally very easily.
But science has been trying to come to terms with it for almost 100 years now, right?
That's right.
So what's the problem? Are we doing something wrong? Maybe are we on a wrong path? Is math broken? Is physics broken? Our understanding of physics? Or is it just a very tough nut to crack?
It's almost even impossible to answer that question, because maybe we don't have the brain power to understand
we have
really what the problem
ChatGPT
is.
right now.
yeah, that's not going to do it. It seems like so far, the brightest minds have worked years of their lives on that exact puzzle, a quantum theory of gravity. And we really don't know at this point if it's just that it's not understandable by us, or not now, or if there is a viable theory out there, it's just hard to test because it involves such extreme situations that it's hard to rule out different models. So we don't know which one it is.
Do you think that there could be a new Einstein moment, that someone comes around and has an intuition how to do it? Or do you think this time it's different? It's not just looking around the corner like Einstein did, to say it very blunt, and have a great intuition. Is this a different situation or similar?
Well, yeah, there's no way to tell for sure until it happens. But in general, science has progressed away from the lone genius kind of idea, which is never completely true. Now discoveries are more made by huge collections of hundreds or thousands of people working together.
Problems are getting too difficult for one person.
Yeah, they're involving more technology, and problems are becoming more complex. The ones we can address now, the simpler things, if you want to call them simpler things, like how space-time works, have been solved in the past, but things are just getting more complex. It's a good question. Yeah, there might just be some missing conceptual leap that we haven't made.
Who are the greatest minds at the moment in that field? I don't know if you heard one of the latest Joe Rogan episodes. He had Eric Weinstein on it, and Eric Weinstein very strangely talked about Edward Witten. But he says that Ed Witten may be one of the great minds able to solve some of these problems.
Yeah, and I'm guessing that's partially based on his discovery with M theory several years ago now. If it seems like if anyone's going to crack the nut, it's going to be someone like him.
Yeah, but I guess there's more people, or is it just a handful?
Well, there are many people all over the world working on this problem, but you don't hear much about them because they haven't had a clear, concrete success that translates to the general public, at least. It's just, it's unfortunate that our ability to conceptualize problems like that, quantum gravity, is so far ahead of our technology right now that we might have to just kind of wait for more and more powerful particle accelerators to help point in the right direction.
I hear that true substantial result comes from particle accelerators the size of our solar system to produce the energies needed to probe the fundamental constituents of what we're talking about. So, I mean, like, this can be ruled out, I guess.
That's what it would take to get to the energies where the problems are, like near the Planck scale.
Yeah.
But maybe there's some clever way to make it happen without investing the entire Earth's GDP into building that.
Do you think that artificial intelligence can come to the rescue? As it comes to the rescue to almost anything right now?
I'm not sure. I mean, a lot of the great uses of AI right now, the clear cases, are doing things humans can do, just faster and better. I have seen examples that are interesting about using AI to predict protein folding, which is something that's very hard for a human to do. So it can definitely expand our understanding.
But not venture into something essentially novel. This hasn't been done so far, I guess, as far as I know.
Yeah, I'm not aware of any good examples, but there's just so much uncertainty with AI, how it will actually be integrated into our society and what kinds of problems it will be tackling in 10 years from now, because things are moving so fast. Yeah.
This brings me to a little theory that has been around for a couple of decades now, and this a theory that's highly criticized, talking about string theory, of course. Some say it's a dead end. Some say people are sacrificing their career, probing ever deeper into that thing. Now, to draw a very blunt analogy, string theory, strings, music. Do you think string theory has something to it when it comes to your analogy, what you're doing? So is this a blunt analogy? Because of course, string theory is not about sonifying the universe or matter. Or is it just a coincidence of terminologies?
Yeah, it's one of those things where the idea itself is so romantic and intuitive and interesting that some people really, really want it to be true.
Yeah.
And after years and years, we can't really say that it is or isn't, and the problem's gotten just much more thorny than we expected. But at a deep level, even without string theory, quantum field theory itself, which is the established, the foundation of the standard model right now, that is already all about waves. It's all about superpositions of of different waves. And so there's
particles are in fact waves.
Yeah. So every particle is also a wave.
Yeah.
And even our description of it is, we describe it as superpositions of different wave signatures. I mean, you can do that with any signal, but that's how quantum field theory is formulated right now. So going one step further into actually imagining like physical strings that oscillate, it's just it's just a very it's a romantic idea. Like I wish it was true.
Is it possible to measure particle waves and then for you to just octave them up to make them heard?
Yeah. So what's a good example? Each particle, you can associate a certain wavelength and frequency. It's called the de Broglie wavelength. And so you could convert a given particle with a given momentum into a given sound wave. And if maybe you had several particles interacting with different wavelengths, you could combine that into some kind of harmony or disharmony. Waves and oscillations are just ubiquitous. That's how our universe is constructed. So there's that answer to that question is almost always yes. There's always some kind of musical analog.
The ancient Greeks, the philosophers, they already had that notion of the universe as a piece of music. So that's very interesting that they had that intuition like 2,500 years ago.
Yeah, I think they were aware that a lot of what we call music is kind of an audio version of patterns and mathematical relationships. I mean, that was Pythagoras' one of his big discoveries, was the secret to music. Secret to musical harmony is simple ratios. And so, of course, they wanted to connect that to the construction of the universe as a whole, because they saw it as obviously ordered and structured and designed is how they were thinking of it in some sense. And so that made that connection between the order and patterns of music, the order and patterns of nature pretty obvious.
Can we hear something
Sure.
else? Absolutely. Now I'm clueless. Absolutely no clue.
Okay. Well, you can probably hear there's a lot going on there. There's different layers of sound.
Yeah.
And so part of it was more sustained notes that kind of morph and evolve. And then there were also transient notes you could hear on kind of a piano sound and some cymbal crashes. So this is another image sonification. So turning visual data in an image into sound. And this is one of the famous images released by the first images released by the James Webb Space Telescope of the Carina Nebula. So the more amorphous sounds we're hearing are representing the contour of the edge of a nebula that's kind of rising and falling in the image, like a mountain range, as we go from left to right. And all the transient notes you heard are stars in the image. So there's one note for every star, and its pitch tells you where in the image it is. As in, higher pitch would be higher in the image physically. So this was part of our set to make the web images more accessible, but also just to create something that people find interesting.
Beautiful.
Sucks them in.
Beautiful. Can we listen to it again? Beautiful. What's your first and immediate association with James Webb?
For me, because I've worked on several image sonifications of James Webb, it's just the picture in my head is just an overwhelming number of stars. The images coming back are just so rich and highly detailed that it actually makes sonification kind of tricky, because there's almost too much going on.
Too much information.
Yeah. Like you can compare a Hubble image and a Webb image, and the Hubble image is pretty and looks detailed, but then you see the same patch of sky with Webb, and there's stars in between the stars,
So in fact, if you had like really sharp eyes, the night sky is not black.
Right. Yeah. Every patch that looks black, if you had bigger
James Webb eyes,
and you held them open for a long enough time, it would not be completely black.
But that's good.
Every patch.
It's very interesting. I mean, like if you go to the extreme, that would mean that the night sky is in fact white, or whatever color it has. But it's definitely not the way we perceive it. We're just seeing the residue of something.
Yeah, you're touching on an old paradox called Olber's paradox.
Yeah.
He was thinking if the universe is infinite and has been around forever, that there would be light in every direction.
Yeah.
But we don't live in that universe because it's got a finite age and it's expanding and accelerating. And so the night sky would not be white. It would just be much, much richer than it appears. There'd be galaxies in every patch of sky you look. But if you had bigger and bigger telescopes looking for longer and longer periods of time, you'd be looking further and further back into time. And so there was a time before galaxies had formed, when there was nothing emitting light. And the time before that would be the cosmic microwave background radiation, which is as far as you can look. So if you had radio eyes to see radio waves, the sky is not black at all. It's radio waves in all directions. Wow. So one of the most amazing things of science is opening our minds and our eyes, in a sense, to all the other types of light that we can collect information about our universe with. And it can look very different depending on whether you're using X-ray eyes or radio eyes. And so to really understand the universe, we have to use all of them in concert.
A couple of years ago, the Voyager space probe left the solar system. There are a bunch of moments that were really critical and relevant, that all of a sudden it left the heliosphere, and then something happened. And scientists even produced a piece of audio from that moment. Can you recall that moment? What happened?
Sure. So our solar system is in a giant magnetic bubble. The sun is putting out a magnetic wind, which kind of clears a cocoon-like structure around our solar system. And when Voyager exited that bubble, there are stronger magnetic fields there, and certain types of plasma waves can travel along magnetic fields. And so it had a detector detecting radio waves and plasma waves. And so it could just directly convert that signal into an audio wave to hear the moment that Voyager exited the solar system.
I think we can listen to that right now. If we listen to it, it sounds also kind of menacing, dark. Is that a coincidence? Is the human imagination overdoing its thing?
Yeah, there's always a little bit of that going on. You can get similar sounding sonifications from plasma waves a little closer to home, such as like near Jupiter or near Saturn. That was just a particularly interesting one because it was such a well-defined boundary. And so there was kind of some quiet, ominous sounds, and then one big burst of very coherent waves that you could hear. It kind of sounded like a bit of a scream, if that's what you're getting at.
Yeah.
Yeah.
Of course, this is what we want, what the media want, because something is screaming out there.
Right.
Screaming for help. Open the hatch. Yeah, fascinating. So where is Voyager right now? It's a pretty old spacecraft, by the way.
Yeah, so there's two of them. They're still going. They're still sending back signals every once in a while, saying that I'm still here. I forget which one. I forget if both have crossed the heliosphere or not, but they're both just after their mission, which was to visit the outer planets. They were just kind of hurled off into empty space, right? No intended target. They're just floating off in an almost random direction, just forever.
The hardware is
partly still alive. It's almost how many years? 77 it was. So it's almost 50 years.
Yeah, and it's it's got less power than a few watt light bulb, but that's enough
it's still
to
alive.
Send it back. Yeah, send back signals.
So it'll be flying for forever, I guess. Where do you think it will ever come to an end? Because it's very unlikely out there to crash into something. So what will happen to the space probes?
They will eventually just slowly erode. I mean, like the Voyager, the golden record on the side of Voyager, it has a lifetime of about 1 billion years. So it's gold, but that'll even erode slowly over about 1 billion years.
Eroding means putting on rust, or what does that mean?
I think in this case, it's mainly just from micrometeoroid impacts, just the small dust hitting it all the time.
Okay.
It'll slowly erode the signal.
Okay.
And so it'll eventually just very, very slowly fall apart over 1 billion.
And produce a pile of gold powder.
Yeah, the record itself, it'll be reduced to gold powder.
And also the space probe. So it will erode into dust, go back into where it came from.
That's true. Very poetic connection. It might take trillions of years, but yeah.
Trillions.
To completely turn into dust.
Yeah.
That's far off.
But trillions of years are way beyond the age of the current universe.
That's right. But as our current understanding, that's a small fraction of the entire age of the universe over time.
Yeah. Let me ask a bunch of very basic questions. So, where does the known universe end? Is there a boundary, and what is beyond the boundary?
The closest thing to a boundary is just the edge of the observable universe. Yeah. So that's the edge of the patch that we have access to, even theoretically, right? Just because it takes time for light to travel. And so we can only see out as far as the universe has been old. So that's the only thing that we can really say is an edge at this point. I mean, we think that's a small patch of a much, much bigger universe. Mm-hmm. And we can put limits on how big it has to be, but we can't even say if that has an edge anywhere. That could be infinite.
How far apart is it?
Right. So the universe is about 13.6 billion years old. And so the furthest light we could see was emitted when it was about 13.6 billion light years away. But since the universe is expanding, that's now about 40 billion light years away. If we can imagine it, it sent its light to us. While that light was traveling to us, that galaxy kept moving further back, further away. And so about 40 billion years in each direction, 40 billion light years in each direction is all we've had any access to.
How does it feel to you as a scientist not knowing what's really going on out there?
Well, that's exactly where you want to be as a scientist.
Really?
You want there to be puzzles that you haven't solved yet.
Yeah.
Gives you something to do, and your employment is safe when there's puzzles like that.
There's two strands in science probing for more information. That's particle physics and that's astrophysics. And so how close to the Big Bang can we go? And are there natural limits to knowledge? And is there a finite moment where we can say, game over, we cannot go any further?
Well, every time we thought that in the past, we've passed the limit.
Yeah.
So we really can't say, but we do know we can quantify our lack of knowledge better now. we can quantify the smallest scales we have any kind of theoretical understanding of, and that gets close to the Planck scale, which is unimaginably small, and it corresponds to an unimaginably high energy that we can't access right now. But I think that's progress, is knowing where those limits are.
What keeps you awake? Not knowing what's out there, or the sheer vastness of work to do still in your lifetime?
Honestly, what keeps you awake is much more terrestrial problems these days.
Climate change.
Even more local, as in housing and family. And when I was younger, most of my thinking time was spent thinking about things that are nowhere near my everyday life, and thinking about black holes and cosmology. But as I've aged, it's, other issues become a little more important on a day-to-day scale when you start to realize the clock ticking.
Well, one question that needs to be asked is, are we alone? So what do you think? Is this a matter of belief, or does a scientist approach that question differently?
Well, all we can do at this point is use what we know about life on Earth and the conditions we're finding and the numbers of planets we're finding and of different types, and at least put some kind of probabilistic limits on the occurrence of life in the universe. So there's still a vast uncertainty in that number, but I think most astronomers that I've talked to, at least, including myself, think it'd be absurd if we were alone.
Someone said it would be a great waste of space.
Right. Yeah. I mean, this is like the extension of the Copernican principles, the idea that we're not in a special place in the universe, not in a special time in the universe. And so if that keeps going, if that keeps going, we're special in many ways, but of course, we make our own meaning and our own special in our lives, and that's through connecting to humans and nature, and so it's not upset about those demotions at all.
Yeah. Matt, I have two unusual questions. Maybe question number one, very easy to answer for you. We have a Spotify playlist for the future space traveler, for the very long and boring haul to wherever they want to travel. Which tune would you not want to miss on that playlist?
I would put Little Wing by Hendrix.
Good.
That whole album to me it's kind of a sci-fi masterpiece, and I associate that with space travel. So even though you wouldn't guess it from the lyrics of the song.
Nice. And last question, and this is the Space Café podcast. It's a coffee place. Sometimes in coffee places, you have an espresso to energize yourself. I want you to share an espresso for the mind with us right now to energize our audiences, inspire our audiences. What would you choose? You can pick whatever kind of topic you want to pick.
It's hard.
You can also pick a piece of music.
Well, I would pick a book, actually, if that's
Sure.
more than an espresso shot. But I think Jonathan Haidt's The Righteous Mind. It's several years old now, but I think it should be essential reading for any thinking person to understand how our evolved thinking actually works and doesn't work.
Beautiful. I think this is a great teaser to now go to your favorite bookstore and get it. Matt Russo, thank you so much for taking the time. This was really brilliant.
My
very
pleasure.
Inspiring.
Thanks for having me.
Super.
Thank you, my friends, for your continued support for this program. Can you take a moment, like right now, for example? If you like what we're doing, why not share a link to the show wherever you're listening to this on your favorite social network? You'll find the link right here, right now, in the show notes. We want this baby to keep growing, and we can only do that with your help. Now is definitely a good time for that. Thank you. And we've got a few really exciting tidbits in the pipeline for upcoming episodes. Until then, take care. Bye-bye.